Black holes are among the most fascinating and mysterious objects in our universe. These are cosmic bodies of extreme gravity from which nothing, not even light, can escape. A black hole can be formed by the death of a massive star when it has exhausted the nuclear fuels in its core and therefore becomes unstable and collapses inwards upon itself. The crushing weight of the matter compresses the dying star to a point of zero volume and infinite density called a singularity. Details of the structure of a black hole are calculated from Albert Einstein's general theory of relativity. The singularity is at the center of a black hole and is surrounded by the event horizon, which is the boundary of a black hole. Past the event horizon, the velocity required for matter to escape from the gravitational field of the black hole exceeds the speed of light so that not even light can escape. The radius of the event horizon is called the Schwarzschild radius, named after the German astronomer Karl Schwarzschild, who in 1916 predicted the existence of collapsed stellar bodies that does not emit any radiation. The size of the Schwarzschild radius is proportional to the mass of the collapsing star. There are many types of black holes, massive stellar black holes being the most common. Only the most massive stars, those of more than 3 solar masses, become black holes after they die. Smaller stars evolve into less compressed bodies like white dwarfs or neutron stars. The other type of black holes have non-stellar origins as they do not originate from a star. Various astronomers have speculated that large volumes of interstellar gas collect and collapse into extremely large black holes at the centers of quasars and galaxies. Most black holes cannot be observed directly because they are small and don't emit light. They can only be observed due to the enormous gravitational attraction on nearby matter, forming accretion disk, which are rings of gases and dust around the black hole. In addition, matter entering black holes become intensely heated and radiates X-rays in large amounts before entering the event horizon of the black hole and disappearing forever. Theoretically, a mass of gas falling rapidly into a black hole is estimated to give off more than 100 times as much energy compared to the energy released by the same mass by nuclear fusion. Similarly, the collapse of millions of solar masses of interstellar gas under a gravitational force into a black hole would account for enormous energy output of quasars and certain galactic systems. One such supermassive black hole, Sagittarius A, exists at the center of our galaxy, the Milky Way. The existence of another kind of non-stellar black hole was proposed by Stephen Hawking. According to Hawking's theory, numerous tiny ancient black holes, possibly with a mass equal to or less than that of an asteroid, might have been created by the Big Bang 13.8 billion years ago. According to quantum mechanics, no matter what happens to an object, its quantum information must be conserved. So even when you crush or break something, its physical properties might change, but nothing alters its quantum information. Then, what about black holes? When an object gets sucked by a black hole, using the black hole paradox, it is assumed that the quantum information of the object being absorbed is stored in the event horizon of the black hole. This shows that the quantum information is conserved, but when more things are absorbed, the size of the black hole increases. What happens to the mass absorbed? The answer is that the black hole evaporates by releasing radiation of these particles known as Hawking radiation. This states that black holes lose mass by releasing Hawking radiation and eventually lose all their mass after a very long period.